Okay, so for today's topic, we're going to start with just a bit of a let's remind ourselves of where we've been so far with this quantum way of looking at things. Okay, so the pathway so far of the quantum model. So Planck looking at the ultraviolet catastrophe, working on black body radiation, right? Again, we say there that he predicted photons. Really, he was just saying if you treat them like it's quantized, the math works, right? He himself did not think it was a physical reality. He would come around, right? But it is a bit misleading for it to say that Planck thought energy could be quantized because he didn't. It just made the math work at first. Okay. So again, the total energy in electromagnetic radiation at a given frequency will be equal to, okay, that frequency times a very small number, Planck's constant, and then times how many photons there actually are, right? So it would be like figuring out the amount of money in all of the students in a room's bank account, right? Take the money per student and then multiply by the number of students, except in the case of photons, they'd all have the same amount of money because they all have the same frequency, right? For a set frequency. So usually we're looking at one photon, and so even on your formula sheet, the energy is equal to h times f. So this is the energy of one photon. This is the energy of all of the photons in a given amount of EMR. So energy transferring energy all at once, like a particle, you either get hit with a baseball or you don't. You can't half get hit with a baseball, okay, is really the basis of quantum theory. It's at least what led us to start to dive into it, okay? So again, the wave's energy is in a clump called a quantum of energy, and when it's acting this way, we think of it as being made of packets of energy, particles called photons. Okay, and Einstein's work with the photoelectric effect, there's no way to explain it without this quantum theory, right? The threshold frequency makes no sense unless light is behaving as a particle. If light is always acting as a wave, then it should be able to build up enough energy over time to kick out an electron. And in the photoelectric effect, it either happens right away or it doesn't at all, right? It's a one-to-one thing. One photon can kick out one electron, particle-like behavior. However, if light was always acting as a particle, there was no way to explain Young's double slit experiment, right? And so we were still kind of in this way of thinking that light must be either a wave or a particle, right? Scientists were kind of understandably pretty slow to get on board with this idea that, yes, sometimes light behaves as a particle and sometimes it behaves as a wave. It is both at once. And when it is acting as one, it is not acting as the other, okay? So that was weird. It should be weird. You should think that's weird. It is weird, okay? Except as we're going to continue to learn, reality is weird, okay? So at the time, those scientists were still very skeptical of this particle model. They really thought if we puzzle on it long enough, I think we'll come up with some way to explain the photoelectric effect using wave behaviors, and then we can still say, okay, light's a wave, no biggie. That was kind of scary for a second. It did not turn out that way. So we're going to look at a guy named Arthur Compton. Now, he thought, okay, well, if electromagnetic radiation can behave like a particle, like this Einstein guy says, then let's try something easier. Let's not worry about this weird, spooky photoelectric effect that we don't understand that well just yet. Let's just look at something we know really well. In fact, something that you know really well, collisions. Because conservation of momentum, that's a pretty straightforward idea, right? The math works, the equations work, it's conserved, it's a law. So if this light is a particle, like Einstein is on about, then it should behave like one in a collision. So here's an analogy, okay? So what happens to a cork if a wave hits it? So let's draw our wave, and we have a little bobbing cork. Now, if the wave is moving that way, what's going to happen to the cork? Well, the wave's going to go by, and this cork is now at a trough. It'll be at a crest. It'll be at a trough, crest, trough, right? As the wave goes through, this is a transverse wave, so the cork goes up and down, right? So what happens to the cork? Right? The cork just vibrates up and down. What happens to the wave? Well, nothing, right? It goes a long way. It lifts up this cork and then it keeps going. So the wave just passes unaffected. What happens to a cork if a particle, like say a rock, hits it? Okay, what happens to the cork then? Well, got our cork and we throw a rock at it. This is what things look like before. And using our chapter 9 knowledge, our unit 1 collisions knowledge, well, we know that momentum will be conserved through both objects, right? So what will happen? Let's say this is a possible path they could take, right? They hit each other and they both are affected. They both kind of bounce off at some angle that conserves momentum in both direction and magnitude. Okay, so what would happen to the cork and the particle? Both are deflected. we can also think, is the rock going to have as much momentum as it did here? Well, no, right? Because now the cork has some momentum. Before, the cork had none. So obviously the rock has given some of its momentum to the cork for momentum to still be conserved. And yes, momentum, also energy, right? But both are still conserved. So we see the rock's path changes, the cork's path changes, whereas versus when it was a wave keeps going unaffected, cork just kind of sits there and vibrates, but particle collisions, boop, boop, both paths deflected in such a way as to conserve momentum and energy. Okay, assuming an elastic collision, which we all know probably wouldn't happen here. In fact, in chapter 9, there were very few examples where collisions were elastic. It's going to change a little bit here. And so Compton was, like I said, thinking about this and said, well, let's study light in a quote unquote collision, because the idea of light colliding was still kind of weird, right? But he said, if it's a particle, it should act like this. It should act like this situation. If it's a wave, it should act like this situation. So just like the cork, if the EMR is a wave, what will happen to the electron? Well, it will just kind of vibrate in the atom that it's part of, right? It'll just kind of get some vibrations. What will happen to the EMR? It should pass by, make the electron vibrate, and then continue on its way. Okay, and then just carry on its merry way. So what will happen to the electron and to the EMR? Unaffected. Keeps on trucking. Okay. But now, what if the EMR is a photon, a particle, acting like a particle? What will happen to the electron? Well, now, let's think about it. If this light is acting like a particle, then in a collision, the wave would come in. I'm going to pause here for a sec. If it's acting like a photon, let's just first think about what would happen to the electron. Just like our cork, the electron should, I'll do dotted for after the collision. Okay, cool. So the electron will be deflected, right? It will also be, now it's going to be flying off, so it's gained momentum and energy. All right, interesting. Okay, gained energy, that one you'll probably have less of a problem with, right? Law of conservation of energy still applies. So if it gained energy, where would it have come from? Well, from the photon, right? From the wave. So let's start there with the fact that the wave is going to lose energy. It's going to give energy to the electron, okay? Difference here from the photoelectric effect, though, it will not be destroyed. Okay, it's going to continue on, but it's going to have to continue on with less energy. What do we know about the wavelength of a photon and its associated energy? Well, as the wavelength gets longer, the energy gets lower, right? Again, I think of it as low energy, chilled out wave versus high energy, anxious wave. And so after the collision, this photon's going to look more like that, right? Longer wavelength, lower energy, because it gave some energy to the electron. So, okay, no problem there. So, why off at an angle? Because that means we're thinking here about momentum, right? But again, we're acting like this is a particle in a collision. So, Compton was thinking, would it do this? If light is acting like a particle, like in particle collisions, it would be deflected, okay? It would lose energy, so its wavelength would increase, right? It would also, now we started with energy because I thought you would have less of a problem with that. Let's come back to this idea here for a sec. Gain momentum. The electron gained momentum. Remember the law of conservation of momentum. If that electron just gained momentum, where did it come from? Well, it would have had to come from the photon. So this is strange. It starts to feel really like, yeah, no, this Compton guy was wrong, right? How can a photon, a massless particle, have momentum? The question asks us to think about what if the EMR is a particle. So we'll play nice. We'll say, okay, well, loses momentum. Okay, that's why it was deflected in the first place. So Compton was kind of saying and probably thinking to himself, yeah, right. It's not going to do this. And then we'll be able to say, all right, photoelectric effect probably has some other explanation. Light's a wave. So what did he do? He took an X-ray source and he sent a beam at a target, some graphite, which is essentially just carbon, and then looked at what came out on the other side. So what did he see? The X-rays scattered in all directions. There's no surprises there. Both the wave and the particle models of light say that when it encounters a barrier, right, double slit, or just the scattering due to collisions, right, they should spread out everywhere, bouncing off of each other. Either way, that should happen. What the model had no way of explaining was that the X-rays came out with longer wavelengths, and therefore lower energies. So it seemed like, yes, the X-rays were transferring energy to the electrons that they were incident upon, okay? All right, so kind of weird, but it got really weird here. There was a clear relationship between the angle that the X-ray scattered relative to its initial path and the change in the wavelength that Compton saw. So for example, as the angle went from 0 to 180, in other words, as you looked at X-rays that were not scattered to X-rays that were scattered perfectly back along the path they came in, the change in wavelength became bigger and bigger and bigger. In other words, they seemed to be losing more and more and more energy, okay, in a particle collision, right? Light was behaving exactly as a particle would in an elastic collision, right? There's kind of a visual of it. So the photon comes in, the electron scattered off, the photon comes in, the electron boing, and the photon goes off with a shorter wavelength. And when we analyze these angles, we see that they always act in such a way as to conserve momentum. All right. So this change in wavelength and deflection together, this whole experiment sort of is known as the Compton effect. So how do we interpret these weird results? The photon that hit the relatively small electrons knocked them out, and the photon transferred energy, and here's the weird thing, momentum to the electron, okay? All that is conservation of energy and momentum. Now I want to pause here for a side note, okay? You might be thinking to yourself, this sounds like the photoelectric effect. It's the same thing. Photon comes in, kicks out an electron. Yeah, that's the photoelectric effect, okay? No, remember, in the photoelectric effect, the photon was completely destroyed, and conservation of energy is really what we apply, right? Not that the law of conservation of momentum is broken, but it's kind of useless for analysis because a lot of momentum is transferred to the metal that the electron was part of, and there's more complex processes going on. So we can only ever really use the law of conservation of energy. The big thing, too, is that the photon is destroyed. In Compton scattering, the photon is not completely destroyed. The photon knocks off the electron, and then it continues. It just does so with a longer wavelength. And in this one, we can use both the law of conservation of momentum and the law of conservation of energy to apply to analysis because both are useful here. And just a side note on this, photoelectric effect, usually with metals, whereas the Compton one, usually with non-metals. Okay, so again, weird. It seems like photons are following the law of conservation of momentum. Okay, so again, Einstein's argument for the photoelectric effect and the particle model of light was strong, but it was such a strange idea, and we were so set on the idea that light was a particle or a wave, not a particle and a wave, that no one wanted to buy into the fact that it could behave as both. Because remember, you can't explain Young's double slit without it acting as a wave. And so scientists thought the photoelectric effect was just this weirdness that we could come up with a wave explanation for. The Compton effect, that is not the case. There's really no way to explain that without accepting that light can behave as a particle. So after the Compton effect, people really had to kind of start to accept that light acts as both a particle and as a wave, okay? So this was the definitive evidence. EM waves may definitely behave as particles. Now, if they collide, they follow conservation of momentum and energy, right? Those are still laws, right? Again, things are getting stranger, but the fundamental physics still applies here. In fact, that's where this strangeness is coming from a lot of the time. So back to chapter 9, momentum is mass times velocity, right? But a photon has no mass. Light has no mass. It can't have mass, in fact, okay? So how can it have momentum? So to derive it, you're going to have to accept this equation for now. We will come back to that in the next unit, okay? For now, just accept that this was an equation Einstein had worked out and had been tested and shown to model reality very well, okay? So the energy of an object is equal to its mass times the speed of light squared. So what we call the equivalent energy, right, is equal to an object's mass times its speed of light squared. Again, for now, just accept this, but if we rearrange it, you'll get to that the mass is the energy divided by c squared. And then if we take that and plug it into our old equation for momentum is mass times velocity, well, we get that the momentum is equal to E over c squared times v. What's v? Now, these are all okay for a photon, right? No mass there. Photon can have an energy. It obviously has a speed of light and a speed. So that brings me to here. Momentum is, since v is c for a photon, then we have E over c squared times c. Cancel out one c and the c squared, and you get momentum is equal to E over c. So on your formula sheet, this is actually written as energy is equal to the momentum times the speed of light. But the energy of a photon is also Planck's constant times its frequency. So we could say momentum is equal to hf over c if you're given the frequency, or you can say, hey, F over c, that's just 1 over lambda, right? Because lambda would be c over f. And so there we go. Momentum of a photon is equal to Planck's constant divided by its wavelength. Now, this is valid if you're given the frequency. However, only this one is actually on your formula sheet. So if you take a look, P equals H over lambda. Okay, now, important to note that don't go trying to find the kinetic energy of a soccer ball you kicked with this equation. There's some weirdness here that we haven't talked about yet that makes this applicable here when we're talking about stuff like this. Okay, we're going to apply it later. Even this step kind of gives you a clue, since V for a photon is C, and that step gave us all of these equations, right? Well, V for a soccer ball that you kick is not C. So you can kind of see how these do not apply to just a soccer ball being kicked. In fact, even looking at this, C is a constant, right? So this would imply that bullet sitting still and a bullet fired out of a gun have the same energy because they have the same mass, okay? It's not energy of motion or anything like that. So don't go applying this to Unit 1 stuff or Physics 20 stuff, okay? It is something that needs to come up next unit to really understand. All right, so yes, these massless photons, weirdly enough, do have momentum, as Compton scattering proves. Okay, let's just try one math example, and then I'll do the rest in an example video. So calculate the momentum of a photon whose wavelength is 625 nanometers. Well, the momentum is equal to h over lambda. So plugging in, I get that it's a very small momentum, which makes sense because we're dealing with photons and electrons, right? Small amounts of momentum, kilogram meters per second or Newton seconds. Okay, so I'll do the other examples in an example video. Let's do this one though, because this does kind of fall under theory. On one graph sketch, total momentum, momentum of the photon, and momentum of electron. Total momentum, well, how does total momentum change in any system? How does total momentum change in any isolated system? Right, and we can definitely consider this an isolated system because of how small and how tiny we are dealing with here, right? So it doesn't change. All right, how's the momentum of the photon change? Well, at first, who has all the momentum? The photon, right? It comes in. So the photon is the total momentum for the first little bit until collision happens and it loses a little bit. Now, what about the electron? It starts out with, out of this total momentum, it doesn't have any of it, right? Until collision happens and suddenly it has some. How much? However much the photon lost. Okay, so now we've looked at quantifying the momentum of a photon. How do we actually quantitatively analyze this effect? Well, everything you learned in Unit 1 would work, okay? You could, even just looking at this diagram, you can start, your ideas are probably already spinning, right? Say, okay, I could find the X momentum, and then the X component of the electron after, and the X component of the Y after, of the photon after, and the Y, and add them up, and it should be conserved in both axes, and that would totally work. Great, yep, go ahead. However, Compton was nice enough to just derive a relationship between the change in wavelength, scattering angle, and mass of the massive particle. So usually that's an electron, not always, okay? And really, guys, all he needed was just really basic fundamental physics and a little bit of algebra and geometry, okay? So he just needed the laws of conservation of energy and momentum, just some geometry and vector diagrams, just a little pinch too of Einstein's theory of relativity. You see that back in that old E equals mc squared that I kind of brushed over for now. We won't derive it. You could, honestly, you probably have all the skills you need to do it. However, they give it to you on your formula sheet. So if you're willing to just accept this, you can kind of see how this looks related to collision angles, right? And how much momentum the electron's going to have and blah, blah, blah. Change in wavelength there, you can see that's really related to the change in momentum of the electron, right? Because P equals H over lambda. So so by looking at the change in wavelength of it, we're getting that from the change in momentum the photon goes through, okay? So m is the mass of the massive particle. Don't put in 0 for a photon because that will never work. You'll get infinity there, right? Usually an electron, not always. Theta is the angle between the photon's original path and its new path. So this is theta, okay? This only works for Compton scattering, okay? And it's just a nice trick to avoid all of the summing stuff up in both axes and setting it equal. Okay, so that wraps up the theory and introduction part of this topic. What's the main point of this? Well, light is acting exactly as a particle would in an elastic collision. When Compton publishes these results, the scientific community, physicists are really forced now to say, yeah, undeniably, light is acting like a particle. But undeniably, from Young's experiment, light is acting as a wave. So what do we have to do? Abandon this idea that light is either a particle or a wave and accept that light is both a particle and a wave. Or to put it in a way that might help you sleep a little bit better at night, light has properties of both particles and waves, but can display one or the other depending on the interaction it's in. So I'll make a video going through the more mathy examples of this stuff. If you want to know which practice problems kind of go with this topic, check the agenda or the Google Classroom.